Aging in place.
So powerful.
Good morning, everyone. Welcome back to Day 2 CoLLAs. I'm very pleased to introduce George Konidaris, who's a good friend of mine and someone we've known each other for a long time, working on very related things. I'm super excited for his talk. He's amazing at combining learning with practical robotics. He's at Brown University, where he's an associate professor. And so we're super excited to welcome George to Philadelphia here for CoLLAs. Thanks so much, George.
Thank you, Eric. You can all hear me? Well, I have to say an obligatory insider joke for people as old as I am, which is, hey, Philadelphia, do you feel all right? Okay, so it's a great pleasure to have see you all here. Thank you for coming at this uncommon hour. I've always appreciated this community. It's the first time I've gotten to come to CoLLAs, so that's so real exciting. Okay, so I'm going to talk about something which I'm going to handily define because I have a penchant for making up names, called the Sensorimotor dilemma. But before we start that, before we start that, I need to discover the range on my clicker. Oh, have I frozen my whole machine? That would be terrible if I did. Okay, there we go. Good. Okay. So just sort of calibration setting here. My research program at Brown is aimed at reintegrating AI. And what that means is that I'm interested in understanding how it is that all of the things that occur in the AI textbooks, like Russell and Norvig, things like reasoning and learning and planning and supervised learning, how those arise in a single agent, okay? Because all of those things aren't things that an intelligence is, they're things that an intelligence does. So I'm very interested in asking the question of how one agent can manifest all of those things. And that is very relevant to the community here because in order to manifest all of those things, as we'll see a little bit later, it turns out that you need to build an agent that lives a very long time and solves a very large number of tasks, which is what we mean generally by general intelligence, okay? So I'm very interested in the problem of an agent that has to live a life rather than solve a problem. Okay, you and I are not problem solvers. Actually, we're life livers. Problem solving is a thing that happens along the way. And instead of being this kind of canonical formalization of an agent where you are a program solving one problem, actually really what you are is you are a much, much more complex agent interacting with the world. Okay. You don't get to interact with problems. You just get to interact with the world, and the world happens to contain problems. And the way that I'm going to think about starting this talk out is I'm going to model this agent, this very complex agent interacting with the world rather than with a problem, as a robot. Okay, and there's two reasons why I'm going to do that. And you don't have to buy either of them, but I like to say them because I think they're true. And the first one is that a robot is a fully realized agent. Okay, so if you look in the first chapter of Russell and Norvig or Sutton and Bartow, you'll see that there's an agent can take actions and receive observations. And that is just a model of what you and I do. And you and I are robots, not computers. Okay. Oh, sorry.
Sorry, thumbs up.
Thumbs up. Oh, good. Yes, you and I are not. We're not computers, right? Because a computer is the artificial analog of a brain. There are no brains in nature. There are no brains floating on breezes. There are no brains hanging in trees. There are no brains frolicking in fields. There are only creatures in nature, and brains are found inside skulls that are used for controlling those creatures. Okay, so every natural agent that you encounter that we're trying to build an artificial version of is a robot, not a computer. As a creature, not a program. Or okay. You don't have to believe this, although it happens to be true. But it is a useful way of thinking about conceptualizing and modeling what it means to build a completely general agent, because it induces this dilemma that I'm about to raise. So when we want to model this agent, we're going to start out with a very complex agent in the world, and the agent can receive observations and take actions. This is all a thing that you understand and know well. The only constraint here is that this observation space is going to have to be the same for all the problems that the agent is going to solve over its lifetime. And this action space is going to be the same action space for all the problems the agent has to solve over its lifetime. Okay. So if you take that and you model it, you say, okay, I've got a utility function that specifies each task. over the course of the agent's lifetime, a human ideally is going to say, hey, I want you to solve this task for me. Here is a utility function expressed in some way like natural language or code from some distribution of utility functions. And then if you take that utility function that's task specific and you add it to the agent's observation and action space, what you get is a decision process model. Okay. So that means that the utility function, the reward function, is a function of the agent's whole history, and the action is a function of its whole history. Its policy has to be a function of its whole history. So this looks like a Markov decision process model, except it's not Markov. Okay, can't be Markov, and in robots, almost nothing is Markov to a first order approximation. So I'm just going to call it a decision process. Okay. And I call this outer loop thing the ego process. Okay, so this is the outer shell of the agent's interface with the world. This is its outer frame. This is how it interacts with the world natively. When you switch on a robot, you get some set of observations occurring at some frame rate, and you get some actions occurring at some frame rate, and that's just what you get. That is just the natural interface to the world. Okay, and that's central. That's like specific to the robot. It's not specific to any task, so we call it the ego process. Now, the thing about the ego process is that it has to be extremely complex. Okay, so when you're solving an individual task, if you were just a computer solving individual tasks one at a time, if you're an agent solving individual tasks one at a time, you get to assume that those tasks are going to arrive with the right frame, with the right observation and action space. If you're playing chess, you get to assume that your input is a 19 by 19 board and your actions are moves, legal moves. Or if you're diagnosing illnesses, you get to assume that your inputs are X-rays and your outputs are illness or no illness. And if you're doing language, you get to assume that your inputs are sentences and text and your outputs, for example, in Jeopardy, are questions. But if you are a general agent, you don't get to assume any of that. You have to do all of this from the same observation and action space. So what you get is you get an observation action space that has to contain all of these observation and action spaces. All of them. Okay, so that's why working with robots sucks. Okay? Because you have to do everything in this really complex observation and action space. You have to. You're doomed to. It's necessary because that is the nature of a general agent. Similarly, we see this all through attempts to do multiple tasks with one agent. Okay, if you want to do the original Atari work, the reason why that was done in pixels to from pixels, big neural network to a joystick is because the pixel space is the only thing in common between all those 52 games. You cannot go and write down like an object space or a state space or the set of objects or the speeds because that doesn't apply to all 52. You have to go to pixels. And actually, it turns out that the action space is relatively small because the joystick is relatively small, but you could imagine that if you also wanted to solve continuous control tasks, you'd have to complexify this joystick as well. If you want to learn to play chess, and you and I wanted to play chess, we could pull alpha-beta pruning out of Russell and Norvig, and we could apply it to a problem, to a chess problem represented in the canonical way as an 8x8 array with 6 types of pieces, 2 colors, et cetera, et cetera. But that's not what a robot gets. A robot gets this. A robot gets a video, HD video, which includes all sorts of extraneous information like, you know, what is the material are the pieces made out of, and what is the angle, and what is the background texture on the wood and the desk upon which the chess pieces are placed, and what are their sizes. And actually, if you look at these pieces, they're not very similar at all. They're only similar in the abstract sense. These positions are all the same chess position. Okay, so it's not a visual compression of these things that gets you to this abstraction. It's an understanding of the rules of the game, which are the states in action. So we would really much rather solve this problem in this abstract space than in this space. So that's the sensorimotor dilemma. Okay. The wider the range of target tasks you're going to get your agent to solve, the more complex the required state and action space, because it has to do the union of all the states and all the action spaces, the harder it is to solve any one task. That's why it's a dilemma, right? The more general your agent is, the harder it is to do one thing. Okay, and this is inevitable, inexorable consequence of a lifelong learning agent. You cannot escape it if you want to solve a wide range of tasks. In fact, I think it's the single most important obstacle to building a generally intelligent machine is that that generally intelligent machine has to be complicated, even if the tasks that it's solving are simple. It has no choice. If you and I want to play tic-tac, we have to go through computer vision to do tic-tac-toe. And that's not an accident. Nature didn't evolve our sense organs to be like ridiculously complicated to take up 40% of our brain just to process for fun. It did that because it's a necessary consequence of being a generally intelligent agent. So the question is, how do you resolve the sensorimotor dilemma? The current best working, and I will freely admit this is currently the best performing solution, is to hit this thing with a giant neural network and a bunch of data. Okay, that just is currently the best performing solution. So my feeling is that in the long run, that's not going to work. And I think that overcoming this is the most important question to getting a general intelligence. So I'm going to propose to you an alternate way of doing that. I'm going to say that we have this robot with a complex ego process, complex observations and action spaces, and then a task-specific reward, or tau. And I don't want to solve this decision process. This decision process sucks. It's really complicated. It has an overblown observation space and an overblown action space. I would much rather solve this up here abstract decision process that contains only the complexity of the task and not the complexity of the robot. So how are we going to do that? And it turns out we know how to do that because hierarchical reinforcement learning tells us we need to do two things to get from this decision process to this decision process. We need to do perceptual abstraction, which roughly in reinforcement learning, you would call state abstraction typically, which means compressing this observation space down to only the minimal task relevant information. And we need to do action abstraction, which means building high-level skills on top of these low-level actions. And if we do these two things together in a way where they're mutually compatible, and I'll talk a little bit about what mutually compatible means in a minute. If they're mutually compatible, you get a well-formed decision process upstairs. And we call this downstairs and this upstairs. And if that works out, if you can make these things maximally compressive, then you can solve this tiny little abstract decision process and go about your day. Now, this is a good thing. So the reason why I said we're interested in reintegrating AI is this decision process formalism turns out to be really powerful. Okay, so if you take a decision process and you start to make some structural assumptions, you can get the rest of AI. Okay, so if you take a decision process and it's observable and it's sequential, then you get Markov decision processes, which we all know and love. And if it's deterministic, known and discrete, you get search, which is like chapter 4 of Russell and Norbeck, roughly. So search is a special case of a decision process, just as MDP is a special case of a decision process. And factored search is just classical planning. That strips. It's also a special case. And if the transition function is adversarial, you get adversarial search. So that's like alpha beta pruning. Right? That's chapter 6 or something like that. Similarly, if you go from a decision process to observable and not sequential, and discrete actions, you get a contextual bandit, which is well studied in reinforcement learning. If you take the contextual bandit and you give it demonstration data, you have classification. And similarly, if the actions are real valued and you have demonstrations, you get regression. So if you look at Russell and Norbeck and you go through it, you get 4 types of things in Russell and Norbeck. You get decision processes, you get language, which is a special case about communicating about decision processes, in my opinion. We'll get to that. That maybe over drinks sometime. You get task-specific things like computer vision is about exploiting the fact that pixels are, lie on a 2D plane and there's locality and translation things. So it's worth studying that specially because it's special and you need it. And then you get tools like first-order logic or Bayesian inference, which are things you'd use to solve a decision process. So actually, you can span pretty much the entire problem setting of that textbook this way. So we can imagine a general formula here, which says that you've got a robot with a complex observation and action space. You give it a task-specific reward function, and it will build a representation that captures the complexity of the task, not the robot. And then it will look inside that representation and say, this representation is discrete, deterministic, known, and factored and adversarial. Therefore, I will pull alpha beta pruning off the shelf, and I will apply it to this decision process. Because that is the algorithm built to exploit the structure in it. Similarly, if it needs to walk around Philadelphia, it might build a map, and it turns out that maps are graphs, so you can do search in that setting. Or maybe it wants to learn to play soccer, and the observation and action space, when compressed, are inevitably continuous. So you get a continuous observation and action space. And you just have to do policy search. There's no way to build a model. That's where you are. But you're going to do policy search at the right level to match the complexity of playing soccer on this robot, rather than at the robot's innate sensorimotor interaction with the world. So going back to this diagram, we need to do perceptual abstraction and action abstraction together. In my lab, we do action abstraction first. We do that because actions are real, unlike perceptions. You can take your perception and you can compress it however you like. You can do whatever you want to do your perceptions. But actions are in a sensorimotor loop with the world, and so you can't do whatever you like with an action. So for a long time, we've been thinking about action abstractions using the options framework, which you all probably know. So you can imagine a robot running around in the world, and maybe it discovers locations in the world it might want to hit. We call these sub-goals. And then it makes a copy of the problem and creates a target for that sub-goal. And then it creates a policy to reach that target. We call that a skill. And then we give that high-level skill to the agent as a thing it can just choose to execute in one execution. Okay, so the options framework formalizes this idea in three things. There's an initiation set, that's the set of states from which you can execute the action. There's the termination condition, that is where you stop, that is your goal. We often call it a sub-goal. And then there's the option policy, which is what you do inside the initiations. And the question for skill discovery generally is, how do you find this termination condition? How do you find your sub-goal target? What we focused on in my lab is this idea of skill chaining, which goes back to 2009, so we've worked on for 15 years, which is a little scary. But the idea is that the point of one of those skills should be that it gets you to another skill or that it solves the problem. Okay, so that means the initiation set of one skill should lie inside the termination condition of another. Okay, you should execute the one skill, puts you inside the termination condition of another. So if you've got a goal, you create a skill to reach that goal, and then you chain a sequence of skills backwards to reach that. The most modern incarnation of this builds graphs instead of chains. This is my PhD student, Akil Bagaria, who's now at Amazon. And what that does, you can think of these nodes in this graph as termination conditions and edges as skill executions. And it will build a graph of connected skills. And then it will pick, using novelty, a point skill on the edge of this graph. It will run to that place, and then it will run an intrinsically motivated reinforcement learning algorithm out and create a new skill. And when you do that, you can create graphs that cover spaces without a reward function, right? So here we've created, I'll show you a video of the ant operating in this maze. It's created a little graph that the ant can use at runtime to reach any point in that maze. So here's the ant, and here is it. Videos are a bit slow. Okay. And here's the ant cruising around. It changes color when it changes skills, and these red dots are goals generated randomly. And what it's done is it's created a spanning graph of this of maze where you can reliably sequentially execute skills to move through the maze. We've also been able to do that in Montezuma's Revenge from pixels. So this is an example of a skill learned for Monty to get the key. First thing it does is commit suicide. And the second thing it does is to get rid of the skull, grab the key. And then the follow-on skill, which you can reliably change from that one, is to commit suicide again and then go through the door now that you have the key. We've also done, this is from my thesis in Ancient, so I won't show it here, but we've also done this on robots, okay? So we've been able to scale up skill acquisition to real robots. It's a lifelong learning question. The robot can solve one task, extract motor skills from that task, reuse that motor skills in a new task to learn them faster, okay? And that's just standard, I think. Okay, so let's talk about the second component, which is going to be the majority of the talk, this perceptual abstraction component. Let's say that I've got some skills, and I want to build perceptual abstractions that are well-formed when combined with those skills to give me a decision process upstairs that I can use for reasoning and planning. Okay, what does the formal process of doing that look like? Okay, so this is a really hard question, right? Like, how are you going to build state abstractions that are compatible with your action abstractions? And the way that we've taken, the approach that we've taken is what we call constructivist, which is to say that we are going to formalize a computational question that you want to ask, and we are going to build those state abstractions so that they're provably by construction able to answer that question. So let's ask the simplest question. We're going to start with a start state in an environment, and we're going to give you a sequence of motor skills. That's a plan that you might want to execute sequentially. I want to execute motor skill 1, motor skill 2, then motor skill 5, then motor skill 17. And you want to answer the question, can I definitely execute it with probability 1? Okay, that's the first question that a classical planning person would ask. Okay, can I definitely do this? And so we can ask, which abstract entities do we need to determine the feasibility of any plan P? It turns out that we only need two entities. One of them is a precondition set. This is the initiation set. This is the name for the initiation set. This is the set of all states from which this robot can press the red button. Okay, you need that. And then you need an image operator, which says that if you start at some set of states, Z, and you execute the option, what is the set of states you could land up in with some probability not 0? Okay, so if you go there and you move right, that's the set of states you might land up in. And if you have those things for both options, then you can plan, right? You can start at some set of states Z. You can ask, can I execute the first option? And it says, yes, you can execute the first option if and only if Z is inside the precondition of the first option. That means there's no place in Z that you can't execute OI from. Okay, there's no state in Z outside of the precondition of the first option. And then you say, where do I land up in? Well, you land up in the image of OI from Z. All the set of states you could land up in executing the first option from Z. And then you ask, can I execute the second option? It says, yes, you can execute the second option if and only if the image of the first option from Z is inside the precondition of the second option. Okay, that means there's no state you could have landed up in that's outside of its precondition. And you can write this proof for any plan. It's an if and only if proof, and it only contains Z, this image operator, and this precondition. And that means, and those things are sets. That means that collection of sets is necessary and sufficient for being able to reason about any plan, being able to compute whether any plan can be executed with probability 1. So what we can do is we can say, I'm going to have an abstract observation. That abstract observation is going to be a name for a set that you could land up in. And then I'm going to add edges like O1 to that abstract action when it's inside an initiation set of another option. That means I can definitely execute option O1 from state S1 when this condition holds. And then I'm going to have S2, which grounds to the same, to the image of executing O1 from the grounding of S1. Okay, so this is downstairs, this is upstairs, and you can prove that this is a sound and complete model. Okay, so you can drop the downstairs, you can drop all the grounding stuff, and you can just plan up in this graph. And you have, and any plan you find up in this graph will work with probability 1, and any plan you can't find won't work with probability 1. All right, now there's a problem there. That graph may not be finite. When is it finite? It's finite when we have something called the subgoal condition, which says that the image of any particular operator from a start set is roughly the same, no matter where you start from. Okay. Sometimes this is an approximation, because this thing is actually, when it's an approximation, this effect set is larger than this image set. When it's not an approximation, it's just equal to. And in this condition, and we construct our skills to have this condition, you get a finite number of edges in that graph. You get a node for each skill, and you get an edge from option I to option J if the effect of option I is inside the precondition of option J. That means you can execute option J from option I's termination place. You can take this set of overlapping chain skills and you can produce a graph, finite sized graph. And this thing over here is the skill chaining condition that I mentioned earlier. Okay, that's why we've been doing skill chaining all this time, is because this thing is well formed. You can't fall off it when the skills are constructed so that you can execute them sequentially. Okay, that's a necessary condition. All right, and then if we want to upgrade that to a probabilistic question, we want to say, what's the probability with which I can execute a sequence of actions? You just need to upgrade these things in the standard probabilistic way. So you take a preconditioned set and you turn it into a probabilistic classifier. What's the probability with which I can execute an action from a state? And you take an image set and you upgrade it to a density estimator. What is the distribution of states I might land up in after executing a state? And then you get this little loop where you start out with a distribution that the robot can be at and a probabilistic initiation set. You integrate over that distribution, that probabilistic initiation set's value, and it gives you the probability of executing an edge. And then that gives you, and then the next thing gives you a probabilistic distribution of next states, and you repeat this process. Okay. And what's nice about that is I can take data in the form of option executions that look like option executions and which options can be run at every state. And I can put that into a fairly generic machine learning pipeline that will discover these skills from data. You can also do this if what you want to do is reinforcement learning. If what you want to do is dynamic programming with those options instead of straight line planning. More or less the same construction holds, except you start with the Bellman equation. Don't worry about that. Just worry about this. This is the Bellman equation approximately for a set of options. If you take that and you think about that an option jumps from a state to a distribution of states, and you can decompose that distribution of states into a mixture distribution if you want. And you say that the value of an abstract state is the expectation of values over that distribution. And The reward is the expectation of values over such transition. You get the Bellman equation upstairs. So what that means is if what you want to do is dynamic programming and you construct your abstract states so that they're a distribution of states over states that corresponds to these images, what you get is you get a system where you're jumping between the distributions that you could be at in the future. Okay. And you can prove that this distribution under some conditions is Markov and value preserving. Okay, which means it's roughly speaking the right observation representation upstairs. You get this graph where every abstract node corresponds to a distribution of states. Okay, so what does that look like? Because it's early in the morning and you should see some videos. So this is a maze. This is what the agent observes. It's an image. It's a textured image. There's going to be some pictures on the wall, and the pictures are going to kind of change around randomly, just for fun. And this agent can move through hallways into the centroid of each room. And what we're going to do is we're just going to execute some movements. Hopefully, I have to click one more time to execute the movements. There we go. And you can see the agent's point of view in this maze. And after executing some number of these, we're going to put it into a machine learning pipeline, and it will construct completely off the shelf a discrete set of states. Each state has a grounding distribution, so you can sample that grounding distribution. So what you're seeing here is you're seeing the agent planning through that state and then generating what it thinks the world will look like when it's at each state. So sampling from that grounding distribution. And you can take this discrete maze and you can plan with it with a graph, because of course it's a graph. It is actually a very simple thing. That's a very simple case. A more complicated, realistic case is what happens when you have a very complex state space with lots of state variables in it. And your actions don't change all the state variables, they only change some of them. Okay, so here's a robot picking something up. In that case, the robot changes the position of the object in its own body, but it doesn't change like whether the door is locked. Okay, so we call this a factored option. Factored option only changes some state variables, but not all the state variables. And you can go through some math, which I will spare you, to show that in this case, the right abstract representation under some assumptions is strips. Okay, so you can retrieve classical planning from the assumption that the actions that the agent is taking are factored. They only change some state variables and don't change all the other state variables. Okay, so just to show you what that looks like, this is an observation image that is given to an agent. These are MNIST digits pulled from the MNIST data set at random, giving its location in a 2D grid. But the agent doesn't see the 2D grid, it just sees the pixels. And it's going to execute up and left and all these things. It's going to notice that these things change. It's going to learn that the problem consists of two different factors. And what it will do is it will split those two factors into two different independent grounding distributions. And then it will run a refinement algorithm to get that thing to be approximately Markov. And it will extract this 2D grid, which it can then move around in using a standard classical factored planning algorithm. Okay. And so you can see it hallucinating its way through this grid, right? So imagining that it's moving then, and then these things are samples drawn from its grounding distribution for each abstract state. But again, you can throw away that grounding distribution and just plan in this graph, and you still get the right answer. Okay, let me show you that done. This is an old video, but it took 5 years to get, so I show it every time I can. Also, I did it myself, and one of my students, so I'm super proud of it. You can tell because the computer vision in it is terrible. So this is a task that I'm able to show this off on a real robot. Okay, so here you have a domain, there's a cupboard and a switch and a cooler. And I just hand wrote some skills to move the robot between the cupboard and the cooler and back again. And to open and close the cupboard and the cooler when it's standing there and has nothing in its hands. And to turn on or off the switch when it's standing in front of the cupboard. Now there's a couple tricks here. So one trick is that when the cupboard is open, you can see the cupboard door there and the switch there, it blocks access to the switch, like it's physically not reachable. Okay. And also when the switch is on, there's a light inside the cupboard that's super bright. And I use an AR tag to indicate where to grasp objects, and that washes out the AR tag. It is like bright white. You can't see anything inside it, right? And then also there's an object, this green thing, which is merrily painted green, so that it's very easy to see in my bad computer vision. And the robot can pick that thing up when it can see it, but when it picks it up, it holds it up here. So and then this robot is going to be given a natural state space that looks like this. It's X, Y, theta in the map. It's a voxelization of the whole room. I've just cut out the cooler, but it's the whole room in one go. And it's its raw joint positions. And now you and I could write down a very small Markov description of that problem, but the robot's not given that. The robot is given this. And then I'm going to give the robot some option executions. It's going to run them there. It's opening the door, closing the door. You can see the light was on there for a second. Here it's opening and closing the cooler and picking up and putting down the object. See, it can't open and close the cupboard when it's got the object in its hand, because it needs both hands to open and close the cupboard, because the base is kind of set back, and so it's sort of doing this. All right, so after about 160 option executions, which is like on average 8 option executions per skill, what we can do is we can run an algorithm that extracts a representation that looks like this up here. Okay, so that is a text file, so it is inarguably symbolic. Okay, it is also provably sound and complete for planning in this problem. And it's got some symbols in it. So it says, if you want to navigate to cooler, your precondition is symbol 1. We can draw samples from symbol 1, and we see that symbol 1 has to do mostly with a robot's location in the maze, and it is standing in front of the cupboard and looking towards it. And then afterwards, its position will no longer be distributed according to symbol 1. It will be distributed according to symbol 0. Symbol 0, here's some samples from it. It is standing in front of the cooler and looking towards it. Okay, so what that operator says is, if you want to navigate to the cooler, you should be standing in front of the cupboard. Afterwards, you won't be standing in front of the cupboard anymore. Now you'll be standing in front of the cooler. Okay, and that's a bit silly, but the robot has learned that distinction from raw data. It has discovered the difference between standing at the cupboard and standing at the cooler, that is the relevant difference, and it's constructed this symbolic operator for planning using that difference. Here's a more interesting operator. If you want to open the cupboard, you have to be standing in front of the cupboard. We already know symbol 1. Symbol 3 is a distribution over the robot's joint poses. Okay, so you remember when the robot's carrying something, it's up here. So this means the robot's not carrying anything. And then symbol 4 is a distribution of the voxels. Now, I've just cut out the cupboard because it's the only thing that changes, but it's a distribution of all the voxels. And this says, you can see the switch might be on or off. There's a bunch of compression artifacts and all other such joyful stuff. But the main thing is that the cupboard is closed. And afterwards, the cupboard will be open. Okay, and all of that is discovered from pixel level data by the robot just by interacting with the world. I didn't tell it that the cupboards can be open or closed. There's no prior biases. Everything is just from raw pixels. And when you give those, these, because there's a bunch of them, when you give the resulting representation to a classical planet, it solves it in 4 milliseconds, because of course it does, because it's very small. And so here's a case where I've asked the robot to pick the object out of the cupboard, out of the cooler, and move it to the cupboard. And so you'll see that it first opens the cooler, but then it doesn't pick up the object, because if it picked up the object, it wouldn't be able to open the cupboard. Then it goes to the cupboard, and then it doesn't open the cupboard because the light switch is on. If it opened the cupboard, it wouldn't be able to switch this light switch off. So first it switches the light switch. Then it opens the cupboard. Then it goes back to get the object. The pauses here are because I'm bad at computer vision. That's not a planning pause. It's 45 seconds to do the point cloud merging. Okay, so that is what you would expect a classical planner to classically do. Okay, it has looked ahead into the future. It has discovered some some logical dependency weirdnesses. It's fixed them, and it's running a plan. And of course, it found that solution in 4 milliseconds because this representation is the natural representation of the task. This task is really simple. What's interesting here is not that it solved it so quickly. What's interesting is that the robot was autonomously able to build that representation. It was able to resolve the sensorimotor dilemma. We can also do things like this for pixels. This is a result which will come out relatively soon. This is a robot learning such a representation for Montezuma's Revenge from pixels. Given skills. Given the jump right skill, it will, using pixels, construct a factored classical planning representation from one. And we've done this in the years since that video. I think we have 12 papers. The last time I counted, 6 of them are on real robots. So this is like a reasonably well-developed framework at this point. The main frustrating thing is that it takes so long. It should really not have taken 160 option executions to learn that if you want to open the door, it should be closed before you open it, and afterwards it'd be open. Right? So we've been thinking quite hard on the other side of the house. Half my lab does reinforcement learning, half my lab does robotics. So that's the reinforcement learning half. Robotics half has been thinking about how we start to make this thing very practical in real robotics cases. Okay? And so what we've been thinking about in terms of a lifelong agent is we've been thinking about the structure present in the world for robots. And when we look at the skills and symbols that we're learning, we tend to find that there's a distinction between things that have to do with objects and things that have to do with space. If you've read Liz Spelke, you know that for infants, objects in space are present very early in their development. they think of those two things separately. In robotics, we also think of those two things separately. There's SLAM, which is for building maps in space, and then there's manipulation, which is for building, which is for manipulating objects. So we thought it might be reasonable to start to break this thing into stuff to do with objects and stuff to do with space. And the nice thing is that stuff to do with objects are things you could learn in a lifelong learning way. Once I've learned to use one coffee maker in principle, or not in practice, I can use any coffee maker that I encounter over my life. I can just walk up to it and know what to do. You know, that works great for showers, for example. As I discovered this morning in my hotel room. But maps are just things that you can, you know, I just walked through this building twice and I built a map, right? We already have technology for planning and maps. We have technology for building maps. All that stuff is easy. So we focused on object-centric symbols. And so the idea is that, you know, when I showed you this operator, I cut out the objects, but that was not actually what happened. So now let's actually say what happens if we're going to learn those symbolic representations as a function of the object the robot is manipulating and separate out the spatial part. And so what we find there is that this is in Minecraft, again from pixels. You can learn lifted symbolic representations of a domain in Minecraft. So what happens here is you like take a photo of an object as if you were standing in front of it, and you learn a representation of that. We can learn this symbolic representation, and it contains some things that change between domains, and those are all spatial. And a special thing we call a linkage. For example, if you turn that light switch, it turns this light bulb on. That's a linkage, and that changes per object instance. But otherwise, you can take this and port it and put it in a new domain, and in a very small amount of time in that new domain, you can learn to instantiate those operators. Okay, so I can just drop this in a new domain and get something like this. This is a planned Minecraft task where an agent needs to craft a clock, which is something my students have tried to explain to me many times, and I still don't understand, but it's got something to do with gold, and you've got to go pick stuff up. And this is constructed zero shot from a high-level representation learned from pixels. It's got to go get some materials, and then it collects them and puts them on this table and does them on the table. I don't know. I've never played Minecraft. But the important thing is that these can be reused across these domain sequences, right? So the agent can learn a lifelong library of action skills interact with the object, and then it can learn symbolic representations that are a function of only the objects, and it can reuse those wherever it goes. Okay, now to make things really practical, we need to get our hands dirty a little bit with real robots. So what my lab has been doing is we've been thinking about how to upgrade the notion of skill and the notion of symbolic representations that are a function of objects to kind of real scenarios. So these things are called composable interaction primitives. They are motor skills for interacting with an object in a forceful contact way that are wrapped with a motion planner, which allow them to be executed sequentially composed. Okay, so that means you can motion plan between them, and you can execute them sequentially zero shot. So those were produced by my grad students, Ben Abadamatero and Eric Rosen. And then what we did is we took the preconditions for every skill, and we said we're going to break them into things that have to do with the object, and you're going to learn those because you can reuse them whenever the object occurs, and then things to do with space, and you're not going to learn those. Those are just going to be constructed at runtime for every new instance. And because we can use a path planner to generate point-to-point paths in a map, it turns out that we can prove, and Eric did this in a 2023 paper, that an action-oriented semantic map, which is a map with objects in it, and then a little region around the object where you can execute a skill, is the right data structure for automatically generating the navigation stack to support planning with portable skills. This is a Boston Dynamics spot with a bunch of motor skills that we constructed for it in a different room. We dropped it in this room and walked through the room once and build a map, and then it can plan to make a cup of coffee in this novel map. And all the navigation skills you see this robot executing are generated at runtime for this one particular map with no learning. And all the manipulation skills were hand-coded by a grad student at great, with huge amounts of effort. Okay. So what's exciting about this is that the agent can learn those motor skills, which are long and hard to learn, and then it can learn symbols associated with them, and that's not so long, but still kind of sucks. But then wherever it encounters those same objects in the world, it can zero shot, build a map, and then reuse them. Okay. This is almost finished. I drink tea, so this is not super useful for me, but my students are coffee drinkers. Okay. The other nice thing about maps is that we know how to resolve partial observability in maps. That's what SLAM is. SLAM is, if any of you have done robotics, simultaneous localization and mapping, that takes a very high dimensional local sensor view of the world and turns it into a Markov XY theta pose in the world. Okay, so it's an abstraction that takes a very high dimensional non-Markov signal and turns it into a Markov signal. So what's the equivalent for space? Well, it turns out that if you want to think about space and objects separately, then you can think about objects being of unknown pose or unknown existence or unknown state. And so my student Max Merlin introduced the idea of object scouting, which is to say, what if you know the map, but you don't know the objects in the map? Can you reason about which objects you should go find? And can you only ever plan with the objects that you know? So it turns out that a property of objects and robots is that when you bring your sensor within range of an object and you can identify it and it's not occluded, you can usually run a perception routine long enough to convert it basically from unobserved to observed. So we call this a locally observable Markov decision process. And we've implemented this observation routine a bunch of times in robots. It's not that hard to do. You just run a next best view on the thing until your certainty about it goes above some level, and then you treat it as if it is observed. And in most robotics domains, you have to observe something before you can manipulate it. Okay, so if you have to observe something before you can manipulate it, then you have a very special planning structure, which is to say you've got your robot and some set of unobserved objects. And the way that you should plan is you should plan only using the observed objects. And if you can't plan using observed objects, then you should find another object to observe, generate one, go localize it, stare at it long enough until you're sure what its state is, add it back to your list of observed objects, and then replan. So this is called a LOMDP planner, and it turns out that it scales much better than ordinary POMDP planning algorithms, to the point where we can put this robot in a map where it hasn't localized all the objects, and it can run around. It can decide, this robot decides that it wants to make coffee, and it's got a whole bunch of unobserved objects there. And it makes a plan that says, it tries to plan for coffee, says, I can't plan for coffee. It picks an object to observe next. There's no valid solution. Which object should I look for next? I'm going to try and find a water cup. And then it navigates around the world looking for a water cup. In this case, the water cup is generated at random, but there's not very many objects to look for. In our software experiments, there can be hundreds or thousands of objects to look for. And we can automatically generate using partial order planning. We can decide which kinds of objects the robot should look for, and then it can use an informed search process to go localize those objects. Okay, so this is going to go to a bunch of locations to see it at each of these locations, which object is there, and it's going to go and observe them. It's got a little, looks a bit like a demagogue, and it's got a camera in its mouth, and so it sort of does that and stares at the object for a second. And then, as I said before, in this little plan outline, there's a next target question, and partial order planning is a relatively well-established planning technique which can find plans that have holes in them. And so partial order planning can tell you in a relatively large environment with hundreds or thousands of objects, which objects you should retrieve. And it scales not that much worse than an MDP. So this is if you had the MDP, this green line here, and this blue line is if you planned knowing nothing about the objects in the world. Okay, so this is going from MDP to POMDP, which is pretty impressive. And this is if you selected the objects at random, and if you try to solve them with a POMDP planner, it's not even on the scale, right? It doesn't even, as soon as you have 100 unknown objects in a POMDP planner, you're dead. But we can scale up to hundreds or thousands using this locally observable metric. So this is a case of a system wanting to make a plan to make toast. And it's got a very large open vocabulary, but it says the first thing it needs to do to make toast is to find bread. So it will go looking specifically for bread. And it won't look everywhere for bread because it's reasonable in real life that you have priors of where objects are. You don't start opening everything at random. Very often humans have very narrow priors. You will go look at the one of three places you could find bread. You will find the bread. You will get the state of the bread. You will decide that it needs to be cut. So if it needs to be cut, you'll have to go find a knife. And then you'll keep running this until you have all the pieces you need to be able to make toast. So in practical robotics land, where we are at now is roughly this. We're at something that we call the envelopes of abstraction approach, which is to say that the world is partially observable and really complex, and there's a lot of weird stuff going on, and you can't do anything. Except in some of those places, you have a map because you've done SLAM. In the places where you have a map where you can do SLAM, you can move freely around. And inside the envelope, and that gets rid of partial observability to do with space, and it replaces it with your pose in the map. That's an abstraction. And then inside the place where you have no space, you'll know some object states. And in those places, you have an object-oriented MDP. Okay, so these are the places where you know the states of objects. And if you hand me motor skills and learn symbols corresponding to those objects, I can automatically produce a task level representation that you can use for classical planning. So we're almost there. We have to do probably about a year's worth of engineering, but we're at the point where if you give me the object-centric motor skills, I can automatically produce the rest of the stack for you in minutes for a new task. So what that does is it focuses the question of lifelong learning on these individual object manipulation skills and on learning their symbolic representations. The learning symbolic representation, we estimate, is about 100 times faster than learning a motor skill from scratch. So that's not too bad. Really, all the effort is going to get poured into learning these motor skills. And fortunately, lots of people in robotics are thinking about that question. All right. So if there's one thing that I want you to take away from this talk, it's this. Lifelong learning agent must necessarily have really complex observation and action spaces because it needs to solve a wide variety of tasks. The observation space needs to support the union of all the state spaces it wishes, of all the tasks it wishes to solve. The action space needs to support the union of all the action spaces it needs to be able to do. That's why you and I interact with the world through motors and pixels, even though that sucks. Okay, but we have to, because if you want to play chess and write poems and juggle and drive a car, you know, and give talks at conferences and type on your computer, and do puzzles and throw balls, you land up at pixels and motors very quickly. That is just the complexity of observation and action spaces you land up with necessarily when you're interacting with the world that way. And that's bad because you really don't want to solve every task in that overblown setting. You really, really don't. So the question that you should keep foremost in mind is, how am I going to resolve the sensorimotor dilemma? If I want to build a lifelong learning agent, how am I going to bridge the gap between this representation of the world and this abstract representation of the task? Because for most of these things, in fact, all of these things, we are about at human level, average human level. We got to average club chess play in like 1975 with alpha beta pruning off the shelf. Okay, we're about as good as, probably better than an average person at Root Finding, at least I hope so, because I use Google Maps all the time. And the average person plays soccer really badly. Okay, maybe the average robot also plays soccer really badly, but we're getting there. Okay, so if you can give me these representations that capture the complexity of the task, more or less our off-the-shelf algorithms are pretty close to doing as well as the average person. It's just bridging this gap that's the question. And one of the things my students haven't studied is how you might do this in a lifelong learning way. How you might, instead of having to learn separate observations and actions for each of these tasks, how you might learn a collection and reuse and manage that library of observation and action abstractions. That seems like a very natural thing to do. I haven't persuaded any of them to do it yet, so that task is still open if you're interested. But this is my answer to how we get around this question, right? It's to learn these observation and action spaces that are task specific, that can be reused, that bridge this gap between the robot's complexity and the complexity of any individual task. Okay, thank you. I think we have a question.
Questions?
Check, check. Okay. Thank you for the amazing talk. I loved it. But about the dilemma, I think there's one thing that you might need to clarify for me. So in my head, coming from like computer vision and classification problems, it sounds a little bit like what you are proposing is to do basically a task inference, because then you have an expert model that can solve this task very well. And where I would definitely agree, like empirically, what has been shown is that inferring this task is equally hard to, like, in the end, your performance will, your accuracy will be about the same, because the errors you're now not making with the expert, you're making in selecting the task. So yeah, what's your comment on that?
Yeah, that's right. So I would say, yes. So first of all, to summarize, I agree with you. What I'm saying, roughly speaking, is that you find this a representation equivalent to what an expert would find, and the robot has to learn it. Otherwise, you're cheating. Okay. And on a real robot size platform, doing that completely from pixels and stuff like that. Like we did it in that one instance, but it was kind of rigid. So the technology is not quite all the way there. But I do think you have to do it. I just don't think that in the long run, learning the representation is going to be as expensive as learning the task. And the reason I don't believe that is partly because I think you can port a lot of stuff about representations, and also partly because robots allow you to cheat, which is to say that you're allowed to exploit structure in the world in the robot, right? In order to make, so on the RL side of the house, you're not allowed to do that. RL people get upset when you do that. But on the robot side of the house, everyone assumes you do that because otherwise the robots would just break on the first day. And so I'm allowed to use things like a pre-learned vision backbone to bootstrap this, for example. I'm also allowed to say my robot can, download all the video data on the internet and use that to learn these things or to bootstrap them, and that's okay. So my feeling is, if you look at babies, it takes them several years to learn these representations, but then they get to reuse them and bootstrap them in a way that becomes very efficient later on. I just feel like you have to learn them. Like there's nothing like chess in our evolutionary history. There just isn't. So you can't be gifted that representation. You've got to build it. And it really is the case that chess players see those. In high school, I played like a fair amount of chess, and those are, when you show those pictures to a chess player, it's immediately obvious that they're the same position, like in, I don't know, 50 milliseconds or something. But visually, they're very, very distinct. So I should say there's more than just the vision, though, right? It's also about the rules of the game, which is the reason that those things are the same. It's not a visual compression. It's a rule compression.
So I will abuse my microphone rights and ask a follow-up. But isn't this like almost then the inversion of the dilemma you're proposing? Like to get to this representation, like you need to map this complex space. So you need the agent that is not capable in the, like, doesn't it go both ways?
Yes. Yeah, but I think it's totally fine to exploit the fact that the agent's got a really rich representation and a long lifetime. In fact, I think it's necessary. So, yeah.
Thank you.
Nice presentation, thanks. So my question is that you haven't really talked about how to actually build the representations. So like the algorithmic part. So the robot must have a lot of priors and.
So, okay. No, the robot does not need a lot of priors. So maybe I zoom past the slide. Hold on, I'm going to click through a whole bunch of them because it kind of looked like a list, and I hate slides that don't have pictures on them. I think it was right after this one. The reason I didn't go through the algorithm is really simple. So for this case, what you do is you just get data of this form. You partition the data so that an approximate independence condition holds. And then you put some of the data into a classifier that maps states to true or false. And you put the rest of the data into a distribution, a probability density estimator. And for that, for the example I showed you with the robot walking around the world, there were no priors. It just used pixel data compressed using PCA. But it just used off-the-shelf sklearn density estimators and classifiers. They're both non-parametric. They were just whatever happened to be in the toolbox in 2017 when I did that experiment. So that's not where the complexity is. The complexity is in building the skills. Okay, so building the skills are much harder than doing, like we're getting close to the point where if you're given the skills, the symbols are, we can just learn them. It's a question as to whether or not it takes 100 or 10 executions or 5 executions. And I think we've got to the point where it can be 5. But the skill learning is very hard. And that's because you're interacting with the world and it's unmodeled and complicated and you don't want to break your robot's fingers and all sorts of stuff. And so that's actually, I think, the right place to put a bunch of priors in. So that policy representation I talked about at the end, CHIPS, is a very structured policy representation. It contains an envelope that assumes that you have made contact with the world and has a bunch of invariants that you want to maintain when you move this object. And has a safety envelope so the robot doesn't tear off its own fingers, and has a termination condition, an initiation set, and a motion planner on either end. That's got a lot of stuff. So my feeling is that the motor skills have to be very structured and can include a lot of priors, but the symbol learning part does not need that. Does that make sense?
And the skills are learned from demonstrations or completely unsupervised ways?
So it depends. What I showed you with the ant running around is completely discovered from data. In practice, they're on real robots, they're bootstrapped from demonstrations or motion planning, typically, because what we find is that if you, even with a very structured policy representation, if you want to learn from scratch, you're looking at hundreds of option executions to get a good policy. And if you use motion planning or demonstration, we can bring that down to between 10 and 30, which feels, for something like opening a peanut butter jar. So that's not, the demonstration part's not so great. Motion planning is okay because you can do that autonomously, but you need to feed a bit of information to the motion planner for it to be able to do that. So those things tend to be done not from scratch. On the other hand, I don't know that humans learn that many motor skills from scratch. I certainly watch my parents do a whole bunch of stuff and learn from them. So I think the motor skill problem might just be fundamentally hard. And at least the sort of beginning and ending conditions are mostly gotten from demonstration. I think very few humans invent completely new motor skills themselves. That makes sense. Thank you.
Great food for thought. To pick one of the questions I have, one of the problems with the symbolic level or even the skill chaining idea can be the explosion of uncertainty as you're modeling forward.
Yes.
So in your example, you talked about like with probability 1, you end up in this state. I think you had something about kind of correcting, making sure to construct the skills such that there was a collapse of probability, like a certainty. And the random pictures in the video, not just for fun, those are landmarks you put in there. So how does that interact? Like, are you able to construct skills such that they exploit landmarks in the state or generate some sense of like, how reliant are you on RFID tags for each thing or QR codes for each thing that are distinct? Take that vague question and go.
Okay, that's a great question. All right, so you're totally right in that. In the general case, what happens is you can think of that image distribution as like a belief of your future state, and in the general case, the belief of your future state keeps growing in entropy. There's just nothing you can do about that, right? So in the general case, you can't construct a finite, and this is just true. You can't generally abstract stuff. You can only abstract stuff under certain conditions. So one of the conditions under which you can abstract stuff is the funneling condition, which is that the initiation set has to be large and the termination condition small. And so one way to think about feedback skills, and this is typically what we have in a robot, these motor controllers, is that they at each motor skill, you use feedback control to try and collapse the uncertainty back. And so if you have that condition, if you have that funneling condition, then the entropy doesn't grow in that distribution as you go forward. Now, in real life, entropy grows a little bit. And one way you can defeat that is you can have feedback controllers. And so instead of a straight line plan, you can have a policy, and the policy can loop you around a few times, and sometimes that can deal with your uncertainty. What we find on real robots, though, is that, the world is happily constructed so that it's mostly not chaotic, and mostly if you apply a feedback controller and some rules, you can get things to the right spot. Plus a motion planner, which can get you to move around without hitting stuff, et cetera, et cetera. And so but that's exactly right. That's like the crucial, like if you can't do that, you can't plan, roughly speaking.
And it is because you have this idea that you're building the abstractions and the skills in order to make the abstract planning possible.
Yes.
That's very cool.
Right. Yeah, so that's why the chaining condition, right? That's why it's been there for 15 years.
I'm behind on my tweet.
Okay, actually, I had a slightly different question, but just a very brief follow-up to Anna's question. Does that mean that you're actually learning, you're updating the policies as you're executing them when you're trying to achieve these termination conditions?
So, okay, so it depends on the specific piece of work you're talking about.
Okay.
In Akil's work, yes, learning is going on all over the place. In the stuff that I showed you where we learn the symbols, just because I don't want to torture my grad students too much, for those, the skills are typically fixed and given in advance. In principle, there's nothing to stop you from doing that. So really, it's a standard model-based RL thing. The model upstairs is wrong. It's always wrong, but it's usually approximately right. And as you get more data, you make it better and you plan with it. And if the plan doesn't work, you just replan. But in principle, there's nothing to stop all these things being learned at the same time. The only thing is that there's a logical dependency between them. It's not a temporal dependency. It's that there's a logical dependency on the property, from the properties of the skills to properties of the symbols. You don't have to learn the skills first, but you do. We have designed the algorithm so that the skills better have those properties when they're finished. Otherwise, the symbols don't make sense.
Yeah, it makes a lot of sense. Yeah, when you said feedback controller, I was thinking either you have a PID that's trying to adapt, or you actually are updating those options to make sure you achieve that. Okay, but I had a somewhat philosophical question going all the way back to the very beginning of your talk, where you say we're not solving a problem, we're living in this world.
Yes.
And so I'm curious for this, maybe we don't always have tasks. Maybe there's points in between where we're just living. It's kind of a philosophical question.
Yeah.
I'm wondering if you could tell me a little bit about your
That's
thought
right. So
process.
Leslie has the same objection. Leslie's like, there's no tasks. And that's, that's probably right. I do think that it's a reasonable way to get a handle on this is to say, okay, a good initial model is to say that you've got a utility function and it switches and you know when it switches. I think what actually happens is people have a bunch of their own internal things which feel like tasks, like, I don't want to be too hungry. I need to be caffeinated at all time, for example. And they're balancing that with external needs, but people are more autonomous than I think we necessarily want these to be. I would like to just tell my robot what to do because otherwise it's not going to make me cocktails, right? And so I think that a good model for a general purpose AI is we're just going to feed it tasks and it's going to maintain itself, and therefore it's going to look like it's piecewise constant in the utility function. I don't know that it's necessarily a great model of people. In the old days, which you were around for and Anna was around for, there was some work on robot motivation systems which thought about maintaining like a robot's homeostasis and stuff like that. I think that's reasonable and relevant, but yeah, I'm just not thinking about that at the moment because enough math to do. Thank you. I hope that made sense.
Okay, that's about all the time we have. Next up is the